So maybe I will share the screen first.
Yep, and let me do my introduction. Hi,
Okay.
everybody. Thank you for joining us today. My name is Aisha, and I'm one of your Solid State Circuit Society staff members. The topic of today's webinar is Webinars for Young Excellence, Experience Sharing, Keep Thinking, Anytime, Anywhere. Get Ideas from Daily Life and Prior Arts, presented by Professor Yan Liu. Today's webinar will be a little over an hour, and we'll hold a Q&A session at the middle and the end of the webinar. Attendees of this webinar have the opportunity to earn a certificate of participation for attending this webinar. I will put a link in the chat box with instructions on how to obtain the certificate. The webinar video and slides will be posted on the SSCS YouTube channel after the webinar. Please use the Q&A on your dashboard to ask any questions. I now invite SSCS Webinars for Young Excellence Committee to introduce our speaker and give a few welcoming remarks.
Hello and welcome. My name is Xiyuan Tang, and I'm an assistant professor with Peking University, China, and also an IEEE SSCS Young Professionals Committee member. I will be the moderator of this webinar. It's a great honor for us to have Professor Lu from Tsinghua University here with us. He will share us how to get ideas from daily life and prior arts. Before we kick off this webinar, I will start with a short introduction of who we are and what we do. As young professionals and students, you make up more than 30% of our overall membership, and you are the future of IEEE SSCS. And as the SSCS Young Professionals Committee, we strive to address the different needs and interests of our younger members with initiatives like this webinar today. So here presents some selected benefits of the SSCS membership for young professional members. You will have the access to the SSCS Resource Center, which contains technical tutorials, short courses, and webinars. You will have the distinguished lectures in your local setting, and there are opportunities to apply for various grants and awards. You will be able to develop leadership skills and make professional connections by becoming a local or global young professional leader. We also have the SSCS Young Professional Networking event at top conferences. And in addition, we have this online mentoring platform. It helps you connect with mentors around the world virtually. The upcoming mentoring event would be hosted in ASSCC this year. It will happen on November the 20th, and it will open to all SSCS members and ASSCC attendees. Since 2020, we have hosted webinars for Young Excellence, which is a quarterly webinar series dedicated but not limited to young professional members. And currently, we have 7 committee members to operate this webinar. We focus on technical tutorials and developments. And these webinars will be available at the SSCS YouTube channel. So today we bring you the webinar, Keep Thinking Anytime, Anywhere, Get Ideas from Daily Life and Applied Arts. So to begin with, let me briefly introduce Professor Lu. Professor Lu received the PhD degree in Electronic and Computer Engineering from the Hong Kong University of Science and Technology, Hong Kong, China in 2013. From 14 to 24, he was with the State Key Lab of Analog and Mixed Signal VLSI, University of Macau, Macau, China. On July the 1st, 2024, he joined the Department of Electrical Engineering, Tsinghua University, Beijing, China, as a full professor with the endowed Xing-Hua Chair Professorship. He has authored and co-authored about 200 peer-reviewed technical articles and 2 books. His research interests include the high-density power converters, integrated voltage regulators, wireless power transfer, and energy harvesting circuits and systems. Dr. Lu has served as an ITPC member for ISSCC, as an TPC member, and then Power Management Subcommittee Chair for CICC, and an IEEE SSCS Distinguished Lecturer. He has served as a guest editor for GSSC, TCAS 1, and TCAS 2. He was a recipient of the IEEE SSCS Predoctoral Achievement Award, the IEEE CAST Society Outstanding Young Author Award, and the ISSCC Award for Outstanding Far East Paper. And if you have any question, please leave it in the Q&A box, and we will have two Q&A sessions. One is in the middle of the talk, and the other one is at the end. So without further ado, let's welcome Professor Lu.
Well, thank you, Xiyuan, for the kind introduction, and thank you, Aisha, for hosting this event, and thank Carmen for inviting me. Let me share the screen. Okay. So you can see this, no problem, right?
Yes.
Great. So yeah, again, thank you for inviting me, and it's my great honor to deliver this talk about how to get new ideas from daily life and prior art. Yeah, since we just had a long introduction, I will skip the first page. So this is outline of my talk today. We will start with the suggestions for how to get new ideas and finding research directions. And then we will talk about some of our selected examples of our favorite works in the past 15 years. And then we will have short break during which we can have some short discussions, Q&A. And then we will continue to talk about how to design a good layout, a good draw, good schematic, and a good figure for academic papers. So suggestions for new directions or new ideas. Actually, when I was just beginning my PhD study, a senior colleague in my lab, in our lab, told me that basically we have two dimensions. One is the application, and another is technique, a problem or solutions. So basically, then we have four combinations: old problem, old solution, old problem, new solution, new problem, new old solution, new problem, new solution. Of course, new solution, new problem seems the best thing, right? And nobody will do old problem, old solution. That you cannot publish paper on that. But one thing I want to emphasize is that actually old problem is not necessarily bad. Actually, old problem means classic problems, right? If you solve some old problem with new solution, that also has a real impact. Those are real problem, practical problems. Like as we are all analog IC designers, we design DC-DC converters, low dropout regulators, A to D converters, PLL, RF circuits. Those basic circuits or converters are basically old problems, but we propose new solutions, new techniques to improve those converters, regulators, transceivers, right? That has real impact, especially economic impact. Those are the practical problems. But on the other hand, if we targeting new problems, that will be easier for our research, right? If you targeting new problem and use some old solution, if you come into this area, if you come into a new problem area early, that you can use old solution to solve new problems, then you can already publish a paper, right? That will be easy for academic research if we target new problems. Of course, if we have new problem, new solution, that will be a very perfect way, right? And then after years of research experience, recently I was thinking, oh, we need to elevate to a new dimension. If we solving new problems with new solutions, we should sum up the solutions and come up with new theory, right? That's another dimension, like shown in the figure. In the past or in the two-dimensional research diagram, we can have old wine fill up the new bottle, or have new wine fill up the old bottle. That's a new thing already. But if we have new theory, new solution, we can have new wines, right? The cocktail wine. We have if you go to the restaurant, the bars, you have a lot of fancy names, new names, a lot of combinations for these cocktail drinks. And we also have a good example from a Chinese company, the coffee called Luckin Coffee, right? They combine the Chinese baijiu. Actually, the Baotai wine is the most expensive wine in China, and then they put 1 or 2 drops into the coffee, and actually it becomes quite popular and becomes a phenomenon event in the advertisement area, right? They have a great success by promoting this product. I think this is a very good solution, and it's a new solution, right? It's a good example. And new technology boosts new idea and paradigm shift, right? We can look at the first example. Previously we have planar MOSFET, and then we have FinFET, and then we have GAA, the gate all-around FET, that give us much better performances that empower the IC designers to do more creative circuit techniques and to design more powerful circuits and systems. So with technology, we can have much more new ideas, try more new ways that those methods may not be feasible in the past. And then we have, right, everybody use ChatGPT, use Sora to convert text to video. It's a paradigm shift. Probably in the future, the director or editor of the movie only need to write the script, and then the AI will generate the whole movie for the audiences, right? Of course, the best movie may still be acted by human beings, but for some popular movie or the animations, they only need AI to do that. So it's totally a paradigm shift. And like the previous product, the DJI drones have already changed the movie industry. We got a lot of shots from the drones in the movie shots. And of course, the robots will help humans to reach some dangerous places and do some difficult tasks that are dangerous for human. And recently we have the Elon Musk proposed the robo-taxi, robo-bus, and the humanoid robot that will change the world. And the EV is basically totally a paradigm shift compared. It's a great challenge for those gasoline car companies. And for the future, I hope we do not need a person like Neo in the very classic movie, The Matrix, to save human beings. I hope we can survive in this wave of AI transformation. And let's come back to ground. How should we do research, and how do we come up with new ideas? We should first prepare ourselves, right? The first suggestion I would give is to study the classic textbooks. We have limited time, but there are so many books. So we need to start with the most classic books, the textbooks, like in analog circuit design, we have Professor Razavi, Professor Willie Sanson, Paul Gray, P. Allen. They are all great professors with excellent textbooks. We need to start with those classic textbooks. And also we need to read the top journal and conference papers. There are hundreds of thousands of papers in our field. So we have limited time. We should focus on those top and highly cited papers to start with. And then that will help us to build a good, solid foundation, background for our direction, for our research. And then we need, after reading the papers, we need to do simulations, right? We need to reproduce those results in the paper. So do not just read the paper. That will not be efficient. We should develop ourselves with an upward spiral path. We need to read paper and then think, simulate, and then go back reading, and then thinking, simulation. So we need to go up with this upward spiral trend. That is very important. Do not like read for 3 months, and then basically we as a human, the human brain is dealing with the memory. We forget things quite fast, actually. If we keep reading, we cannot remember so many things. But if we do things, we do simulation, we can gain those knowledge, and then those knowledge will keep in our brain. And then it's important to discuss with talented people. Discuss with your advisors, colleagues, and peer students, and have lunch or coffee with them occasionally, right? So it's also important to get physically closer to talented people. That's why we stay in the same lab. And it actually, one phenomenon I observed is actually in our lab, if two students sit together, they can actually, they can communicate very well. 1 meter and 5 meter difference within the lab will make a lot of difference. If two students sit together, they can communicate. If they have problem, they can talk within literally 1 second. But if they sit 5 meters away, probably those 5 meters will already stop them from communicate with each other. So not to mention if you are like 1 kilometer, 2 kilometer away from another colleague. So quite important to get physically closer to the talented people. And we should attend conferences, workshops, seminars, and ask questions. So by asking questions, it pushes us to summarize the logic flow of the talks, and then to communicate with people, and then exchange ideas. One last thing is we should ask for help when we spend a lot of time to solve one particular problem and still cannot solve it. That's also the reason we stay in the lab. It depends on how the size of the problem. If it is a big problem, like your thesis, probably you should spend months to solve the big problem. But in the daily work, we may have some small problems. If you spend a week or a day for some small problems, that probably sometimes other students have already solved it. So we should ask, and then to save a lot of time. Sometimes it really depends on experience. So it's important to discuss with people. And then we also need to talk to ourselves, right? We need to think about our design when we were running, right? Actually, running is the best exercise after work, because running is actually this is what Professor Willie Sanson told me when he was visiting Macau. Actually, running is the action for escape something, right? When you fear something, you escape and you run. So when you are running, you feel happiness. So running is a very good practice. It brings you joy, and you can talk to yourself during running. And you may talk to yourself when you take shower, before sleep, after sleep, right? Different people have their different best timing. Some people have their brain run faster before sleep. Some people's brain runs faster after sleep. And then we can think about ideas when we taking buses or the metro, the subway. Of course, do not think about your design when you are driving. That's dangerous not only for yourself, but also for the people on the road. So a short summary for getting new ideas and finding new research directions. We talk about 3 dimensions: new application, new technique, new methodology. Of course, a 3 new work would be perfect, but that will be a rare one. We should be very lucky to work on really new application, and then get really new techniques, and then come up with a new theory. That's too ideal, right? Afterwards, our research, our engineering, modern engineering discipline has been thousands or hundreds of thousands of people has been worked for hundreds of years already. So it's very hard to get these 3 new work. But I would say one new work is sufficiently good. If we are targeting a new application, or we have a new solution for old problem, or the best case is we also come up with some new theory, that's already a very good work. And the new technology boosts new ideas and paradigm shift. So we really need to embrace the new technology and try to solve, try to adapt to the new technology. We need to prepare ourselves with an upward spiral path, learn from the best, talk to ourselves, and discuss with smart people, right? So that's basically the suggestions for getting new ideas and finding research topics. That's the first part of my talk. And then I will share some of the examples, our favorite examples that we done in the past 15 years. The first one is a DC to DC converter ring. But before that, I would like to briefly introduce what does power management do, because I suppose most of the audiences may not working on power management IC. Probably we have a wider range of audiences. So I consider myself as a cook. Basically, as a power management IC designer, we cook the raw energy, the raw meat materials, and then turn them into delicious food, new dishes. And then we serve different customers, like the CPU, GPU, display panel, sorry, and memories, USB. Different customers have different appetites. So we need to adapt to them. We need to cook the dishes, adapt to the appetites of the customers. One direction we do is switch capacitor DC-DC power converters. It also called charge pump. But this charge pump is not the charge pump integrator used in PLL or other feedback loops. It's really a power converter that pumps the energy up and down. Okay, so we use the fly capacitor to transfer energy. So we can consider the fly capacitor as a cup or a bottle that move the water from the source to the load. And on the load side, we have a filter, which is the filtering capacitor that give us smaller ripple. We have the load current draw current from the capacitor. And we may have a bottleneck if we switch too fast. So how to improve the output capability? If we want to deliver more current, our controller can change the frequency, right? If we move faster, more frequently, we can deliver more energy. And also, if we have a larger cup, larger bottle, we can deliver more water at one time. We will have a bottleneck if we switch too fast. That means we need to design the size of the switches properly. Okay, so basically there are three ways to change the output current or output capability. That is the capacitance, switching frequency, and the size of the switches. If we have one bulky converter that have only one phase of the capacitor and the switches, we will deliver a lot of energy at one time, right? This is also called hard charging. When we short two capacitors with switches, there will be large inrush current when we just turn on these switches, because the capacitors have large different voltages, and then they have large VDS on the switches. So we will have large glitches, ripples. That will be the wasted energy, because for the digital load, any voltage higher than the minimum voltage required can be considered as wasted. So reduced ripple is also quite important in terms of system efficiency. So one popular way is to cut the large piece into small pieces and then operate them with the interleaving phases. So they deliver energy one by one with small time interval, similar to eat a pizza, right? We cut the large pizza into small slices and eat one by one. And then we can get small ripple. And about 10 years ago, this multi-phase interleaving is a quite popular research topic. So when I was visiting the Vatican City in 2013, more than 10 years ago, when I stand on the top of the church, I look at the square with hundreds of columns surrounding the square. After I go back on the train, I'm thinking, because it's quite popular, right? At that time, the multi-phase interleaving is quite popular. I was thinking, can I design a multi-phase interleaving converter with hundreds of phases and surround the load in the square? We can design a converter ring to surround the load. So that's so this is what I did when I was a postdoc in 2014. So this is the converter ring with, on the top edge, we have 30 power converter cells, and on the other edges, we have 31 cells. Actually, the number of phases is flexible, is layout dependent, right? How many cells we put is depends on the layout, the size of the layout. And then we put the input and ground pads on the four corners. That will not block the other pads from bonding out, from being bound outside. And we have the load in the square, right? And because the input and ground pads are on the corners, so the original chip can still normally bond out without problem. The benefits is to reduce the IR drop and the supply variations. We will suffer from parasitic resistance and inductance if we have a long distance between the on-chip supply and the point of load. If we have power supplies from 2 sides or 4 sides, obviously we can significantly reduce the parasitic resistance and inductance. So our idea is not only about layout, right? We should not publish one paper for layout innovation. We also have a circuit level innovation. Because of the multi-phase interleaving operation, we can actually consider that the switch capacitor power converter is a pseudo-continuous time power stage, that the high frequency signal can still pass through this slow switching power converter stage. We try to design the dominant pole at the output and design high frequency error amplifier buffers and convert voltage to frequency with the VDD controlled oscillator that can change the frequency of all phases instantaneously. And we have power converter stages with multi-phase interleaving operation and convert frequency back to voltage. And for this complete feedback loop, we have the bandwidth exceed the switching frequency of the power stage. So we also did some simulation to verify this idea. Here we can see we apply here a 150 megahertz AC signal to the switching power converter. And the switching frequency of the power stage is only 33 megahertz. And we can see on the output node, the 150 megahertz AC signal appears on the output smoothly. So that verify actually a very high frequency AC small signal can still pass through this low frequency power stage. That breaks the Nyquist theorem actually, right? With this multi-phase interleaving operation, it's a pseudo-continuous power stage. So by doing so, we can design the dominant pole at output and increase the bandwidth, achieve fast response without additional gigahertz clock frequency. So this is a pseudo-continuous time power stage, and the UGF, unity gate frequency, is actually higher than the switching frequency, a couple of times, several times higher than the switching frequency. This is the chip micrograph. At that time, about 10 years ago, we used 65 nanometer low leakage process. We have a converter ring with a size about 2 millimeter by 2 millimeter. And actually, we didn't waste the middle area. Actually, you can see in the shaded area, we have 3 other designs included in this square. And we have the converter ring surrounding the square. Actually, the 4 designs on this chip are eventually all published on ISSCC or JSSC. So this is a very cost-effective chip that we designed in HKUST. And then we talk about, we want to introduce a series of reconfigurable bidirectional wireless power transceivers. That is one of our major research directions. We came up with this direction when I was talking to a master student, actually about 10 years ago, 2015. In my office, I talked to a master student. We think about the research direction, and then we talk about, can we invent something to use your phone to charge your girlfriend's phone? Okay, so wirelessly. And then we think about that. Actually, we can, without adding additional hardware, we can turn the wireless power receiver into a wireless power transmitter. We can reuse the power transistors, the LC resonant tank, and then form this wireless power reverse charging. Although it sounds like not a new idea nowadays, but if you remember, actually the first phone with reverse wireless charging is the Huawei Mate 20 Pro, which was launched in 2018 October. So, but actually we think about this idea in 2015, and then we published this on ISCC 2017. In terms of circuit design, we want to reduce the number of stages and then to improve the total system efficiency from one battery to another battery, right, to improve the user experience. So by combining or reducing the number of stages, we want to achieve a higher total system efficiency for the reverse wireless charging. This is the first work we done for this reconfigurable wireless power transceiver, which was published on IEEE 2017. This is a differential Class D PA on the transmitter side and driving the LC tank. On the receiver side, we have the cross-connected full-wave rectifier. It's pretty symmetrical and simply beautiful. Differential PA gives us higher peak-to-peak output amplitude because it's a differential operating. And the receiver side, we have the cross-connected active rectifier, achieving high efficiency. And then for the second work in this wireless power transceiver series, we proposed the cross-connect. We use the cross-connected power transistor also on the transmitter side. For the differential PA, we found that actually we can save a lot of switching power by doing so, because the parasitic capacitance of the huge PMOS transistor, these power transistors have huge parasitic capacitance. So these capacitors are charged or discharged by the LC resonant tank. That means that the parasitic capacitance will be part of the LC resonant tank. That saves a lot of switching loss. And also we have a better gate control, the gate drive control. We have did some impedance tuning. We achieve 0 voltage switching for the transmitter side, so we can further reduce the switching loss on the transmitter. On the receiver side, we have the cross-connected full-wave rectifier. So we actually get a quite high peak-to-peak end-to-end efficiency. From one battery to another battery, we get 80% total efficiency. So that's why we got published on ICCC in a consecutive year. And then this work was designed by a master student. He is now doing his PhD in UC San Diego in Professor Patrick Mercier's group. So actually he came up with this idea. Interestingly, he combined the full-wave he split the full-wave rectifier and combined it with hybrid conversion concept, and then to get a what we called split dual path hybrid quad path step down rectifying conversion wireless power receiver. So the idea is we consider the LC resonant tank, which is receiving the wireless power, where we consider it as the river source. Is it on the high mountain and a slow mountain that the snow melt and the current come out, right? And then we split the full wave rectifier into 2 paths, and each path combined with the hybrid conversion concept, we have inductor connect to ground, actually also the current will come from the ground, similar to water. The water also come from ground, right? And we have the flying capacitor and the additional inductors. We have 4 paths that all goes to charge the battery. So all the rivers goes to the sea to charge the battery. And usually we want to avoid using inductors, but here we have 2 inductors that share the currents. And in this hybrid conversion, the inductor only conduct part of the current. So the size and weight of this inductor will not be large. Actually, we use really small surface mount inductors for this topology. So you can tell from this schematic, although you may not fully understand the operation of this rectifier, this wireless power receiver, but from the concept, from the schematic drawing, I would say you can believe this is a good design, right? You just look at the schematic, you can tell it makes sense, I would say. And in terms of operation, actually it gives us better the maximum output power when we have 50% duty cycle for each phase, right? For one phase, the current goes in the lower path, and then in the high path, in the high side path, the inductor current goes to output, and then lower path we have capacitor and the inductor, and vice versa. In this 50% duty cycle, we obtain the maximum output power. And we also find that the wireless power receiver can be reused for cable fast charging as well. In the cable charging, it's also a popular idea recently that is to reuse the cable inductance as the power inductance in the DC-DC converter. If we consider this cable as a power inductor, we can get an inductor first hybrid DC to DC converter, and then we can reuse this part of circuit. Those are bulky circuits, right? These are large transistors and the large fly capacitor and inductors. So we can reuse those power devices components to do fast charging as well. So by combining the cable charging and wireless charging chips, we can actually save a lot of area and cost in the devices. So in this direction, the wireless power bidirectional wireless power transceiver, we actually did a lot of works. You can see from the list. We start this direction in 2015, and then we have the generation 1, which is a direct single stage conversion without voltage conversion function. The generation 2 is a hybrid conversion with voltage conversion. So we basically want to increase the power and efficiency at the same time. We need to boost the AC voltage on the coil to reduce the power loss on the coils. So these are the works we done in this direction. And then the last one will be a very short introduction. It's a USB voltage regulating cable. The problem we want to solve is actually during fast charging, our device the temperature goes up quite rapidly when we have the fast charging. So we want to solve this thermal issue. And another issue is actually sometimes we use the cable, use the notebook to charge other devices. So for this cable, most likely we need bidirectional step-down conversion. Right? Previously we mentioned if we reverse operate the converter, usually if it is a buck converter, it's a step-down converter. If you reverse it, it will be a step-up converter. So we need new design to get a both side step-down conversion for this cable. And our idea is to move the charging circuit, the DC-DC converter, the charger, out of the device and move it onto the USB cable. So we need a really small solution to integrate this converter onto the cable connector and reuse the wire as the power inductor. So you can see from this measured figure, the cable actually becomes a heat sink because first of all, it consumes power, right? And then if we redesign the package of the connector, the cable, and then the package of the cable can turn into a heat sink. And the source of the heat is actually the power converter. Right now, actually, we move it to the connector, so it will be a new application, and we need a lot of new solutions if we really move the charger onto the cable instead of inside the device. Okay, so this is a prototype work. We have this a converter with 5 switches, 2 capacitors integrated on this cable connector. So we can have bidirectional voltage conversion. And we also quite lucky to get several papers got accepted by SSCS 2025. In particular, I want to recommend 2 of our works. The first one is a bidirectional dual-path boost-buck hybrid converter for high-voltage power transmission cable in lightweight humanoid robots. We want to reduce the weight of the cable in these humanoid robots. The second one, we name it as HOOP, a scalable hybrid DC-DC converter ring for high-performance computing. You can tell from the PCB design, we really have a converter ring that can provide high current with high efficiency to supply the microprocessors. And if you play video games, you know recently a very hot popular game, video game is Black Myth, Wukong, and we named this design as HOOP, right? It's Xing-Hua, right? That's the hoop of the monkey. Okay, so we can have a short break. Now we can take some questions if we have, and then we continue to talk about the some how to design a layout, schematic, etc.
Thanks, everybody. I just wanted to say the chat is acting a little funny, so if you could add your questions to the Q&A section, that would be great.
Thanks, Professor Lu, for the very nice introduction of your prior works. And for the audience, if you have any question, please leave it in the Q&A panel, and we will ask Professor Lu that. Okay. Maybe due to the we get one question from the audience. How do you encourage people to collaborate with you?
Yeah, you can send me an email, and then we can discuss the technical details if we have common interest in the research directions. And if physically possible, you can visit my lab, right? You can be a visiting student, or you can join or visiting scholar in our group. And I welcome you apply PhD or postdoc, or we can have collaborations in different dimensions, different areas.
Okay, that's all. Yeah. I think that's great. Just wondering, if you want to collaborate with others, how do you convince other people to collaborate with you? Like how to encourage other people to collaborate with you?
I think for collaboration, the very important thing is we should have a common goal. We should have a common interest, right? If we really want to work, we have some really interesting ideas, and then maybe the idea come out during our discussion. So in many cases, actually the ideas come out during the discussion when I communicate with my students. Actually, sometimes the student bring ideas to my office, and sometimes I think about new ideas during running, taking shower, and then I talk to some master students. Okay, I think this is great. You may try that. But usually the PhD students will have their own ideas. But sometimes during discussion, we will have even more interesting ideas or refined ideas. Yeah, discussion is important. Yeah, I think that's.
Okay, that's great. Yeah, maybe one more question for this break session. Audience asked, how do you find the new ideas from your hobbies or the culture? Like, for example, one of your projects uses the idea of all rivers flow to the sea, right? Like, how do you find the link? Like, how to get new ideas from hobbies or the culture?
To be honest, actually this idea, this is this work for this work, the name come after the design. Actually the yeah, the student come up with this idea, and then when we write the paper, I look at I come up with this idea for the name only. When I look at the schematic, it's quite interesting that we have different current, several paths, the current flow, and the current goes from high voltage to low voltage. Yeah, actually, if you imagine the circuits with current with rivers, you may agree with this name. One thing is that for beginners, we have KCL, we have KVL, but many beginners mainly focus on the voltage, and actually in most of the cases we should consider the circuit with the current flow. So if we imagine the current flow here, yeah, then it's from the high voltage to low voltage, from low current to high current. It's quite similar to this the Chinese saying by Chuan Gui Hai, that all rivers flow to the sea. So it's just a name, okay.
Okay, I totally agree. And due to the time limitation, let's first conclude the breakout session, and we would love to hear more materials from your side, Professor Lu.
Okay, yeah, thank you, Xian. Let's continue the second part. We will talk about how to design good layout, schematic, and figure for papers. Like we just introduced, the square is art, and so does analog IC design. Actually, we can borrow a lot of ideas from the existing beautiful architecture of the buildings all around the world. They are all human wisdom, right? And for the layout, we should draw the power lines wide and bold, like the Highway 101 from San Jose to San Francisco. Thousands or tens of thousands cars, people travel between these two cities every day. So this highway is really wide, and is for high current. And do not produce bottleneck. Your capability is limited by the bottleneck. No matter how wide you build your roads, if you have a narrow bottleneck, your current will stuck. So it's quite important to check all the metal layers before tape out to check if you have the bottleneck in the layout for the metal layers. Usually we know we need to draw wide metals, but sometimes you with enough space you will draw wide metal, but sometimes if you plan late, you will have to draw some narrow metals for high current, but that will be the bottleneck, the problem. So we need to build the main roads first. We need to plan the power line first, like the Shenzhen city in China. It was built about 40 years ago. You can see the picture on the left. About 40 years ago, they already planned the very wide main roads. And if you visit Shenzhen recently, you will find that the traffic in Shenzhen is still reasonably good, although sometimes they also have traffic. But compared to Beijing, Shanghai, Guangzhou, other larger cities, Chengdu, Chongqing, I would say Shenzhen's traffic is already much better than other cities in mainland China. It's important to plan first, plan the main roads first. And here shows a map of city with 400 years history. And you can tell from the map, you can guess which city it is. Many roads were built 400 years ago, so it's very hard to add new ones, and it's actually built on a mountain. So again, then it's add additional difficulties to plan wide and bold roads. But people are very smart. Actually, with those the narrow roads, although some roads has two lines, they use one-way roads, which is more efficient, right? If you have two lanes, two lines, if you plan two-way roads, you may have additional conflict between the two ways, right? And actually, one-way roads are more efficient. All the current go in one direction without what is called the thermal noise, right? And also, roundabout is an efficient way for the intersections of the road. It's continuous. When the car goes onto the roundabout, they have higher priority to use the road, and then they should exit the roundabout when they goes to the exit corner. But in the heavy traffic condition, a traffic light will be better, right? If you don't have traffic light, all the cars will be stuck on this roundabout, and then this will be stuck. So in light traffic or medium traffic condition, the continuous operation of the roundabout is more efficient, and in heavy traffic, red light is more efficient. The traffic light is more efficient. So a hybrid solution will be better, actually. So actually in Macau, we have some traffic light and also have roundabouts. So hybrid solution will be a better one. And a compact layout will be more efficient. Do not draw a layout that is larger than necessary. Sometimes especially for research students, the professor has some area that's larger than you need it, and sometimes we have a block, and then only 1 or 2 students needs to tape out, so you have a large area available. So then you draw a larger layout, but that is not good for for performances. A compact layout results in high speed and high efficiency. I have an example here that is the campus of Hong Kong UST. It's a beautiful campus, and it has a huge compound, a huge complex building, contains everything. You have offices, labs, canteens, gym, badminton court. You can take shower after gym and then go back to your lab within 5 minutes. You can have food, go to canteen within 5 minutes. You can talk to the professor within 3 minutes. Again, so physical distance is very important. So it's a very high density. It's a high density talent. Yeah, high density space. It's more efficient, okay, and productive. I think that's one of the reasons that Hong Kong UST published so many good results in the past 30 years. So a summary for analog layout, we should plan first, floor plan first, important signal and the power line first. We should plan those important things first, and then draw the other not so important route later. A compact layout can reduce the length of the routes and reduce delay. For analog layout, we need to have symmetrical layout, right? The dummies does not cost us too much area. Actually, the most area consuming components are capacitors, inductors, pads. So the transistor, the dummy transistors really don't count too much area. So add as many dummies as you can. Pay attention to current directions. If you want to match the currents between different transistors, different direction will actually draw induce different electrical characteristics for those transistors. And draw layout like a schematic. Draw a schematic like a layout. So that is very important. That means you follow the electrical property of the circuit. You follow. You know, sometimes when you draw a schematic, you know, okay, these two transistors needs to be matched, and you draw the layout. You understand, okay, this metal should be wide. This transistor should be symmetrical. It's important to do this. That means you understand your circuit better. Similarly, when we have the guidelines for schematic drawing in Cadence, we should follow the electrical properties of the circuits, make people and the future yourself easy to understand. Sometimes you draw some messy schematic, you think, okay, I can understand it, but consider 5 years later, after you have designed 10 circuits or 10 systems after 5 years, when you look back, you may not remember what you have done 5 years ago. So it's important to draw a very good schematic and make people to easily understand. Draw schematic in Cadence like those in Microsoft Visual. So that's used for the figures in the papers. So it's also important to draw a beautiful schematic in Cadence. And this is a detailed suggestion. Every detailed members should be seen when you press the button F, right? In Cadence, when you press F button, you see the full screen schematic, the full schematic, and we should make the schematic small enough that all the numbers for those transistors can be seen. That will be easy to debug. Okay, that will be also beautiful. Draw a schematic like a layout, draw a layout like a schematic, draw it with love. Because this is your circuit, right? You should love your circuit. You invented the circuit. That's your baby. You love your circuit, and you should draw the schematic layout and the figures with love. Again, for guidelines for figure drawing for papers, following the electrical properties of the circuits, make people easy to understand. Some detailed suggestions. Do not use the Times New Roman, which have sharp edges, which does not look good in figures. We can use some fonts, the Calibri Arial and Arial Narrow, that has smooth figures, smooth characteristic. Use large font size, less different font sizes, bold text looks better. Use less colors. We'll talk more about these 2 points in the later slides. Simple is the best. Draw it like an art. Okay, if you have good figure, the chance of being acceptance will be much higher. I can promise. Draw it with love. Love your work, right? And yeah, like we mentioned, use less colors, less different font sizes, bold texts. 1 or 2 colors to highlight innovation is good enough. At the most, 3 colors in a figure. Okay, here I use 3 colors. If you don't know how to choose colors or don't know where should I put colors, actually black and white and plus gray color is also an excellent choice. Okay, so you can, it's decent. If you draw a schematic with black and white with gray, it's also good looking, no problem. Not necessary to use colors. But if you want to use colors, here are some guidelines for selecting colors. There are analog colors and digital colors. Although we live in a digital world right now, all the colors we look at right now is digital colors, but some colors are actually come from the analog colors, right? They are digitized. Those analog colors looks richer and more expensive. It's literally more expensive in the old times because in the painting, the expensive pigment is actually made from rare natural materials. They are really expensive and they are good looking. And some examples, the analog color are beautiful colors from nature, like the burgundy red is from the color of the wine. And the rich people use these colors. You can tell they are good looking. And the digital colors are simple and looks cheap, right? Simple is the best. Like in this Chinese culture painting. In Chinese culture painting, we just use carbon and silicon to draw this art. Okay, but you can feel the depth and the beautiful things. And we should have a good name for our proposed technique or topologies. The name should be precise and accurate. For example, these are the names we used in our works: analog assisted digital, AA digital, DC-DC converter ring, wireless power transceiver, voltage regulating cable, split dual pass, hybrid quad pass, S2, H4. And we have some examples in the industry, like the AMD Zen series processor. Actually, the word Zen comes from the Chinese culture, right? Means simple is the best. And we have Italian from Intel, Ponte Vecchio. I checked the dictionary. That means the old bridge. So that's the name for this chiplet system. So I think this name is also very accurate. Like, although I'm not sure why Intel picked this name for this system, but for my guess, is that the system is quite similar to this Ponte Vecchio. It's an old bridge with multi-floors, multi-layers. It's quite similar. You have for the chiplet system, you have interposer connecting different chiplets and build this 3D system. But do not invent names for existing techniques. Use the existing names. Otherwise, it will confuse people, and then we do not publish paper with new names, right? We publish paper with new techniques. So only invent names for new ones. Okay, I would also like to recommend some talks on this YouTube channel. You can subscribe the IEEE Solid State Circuit Society YouTube channel. We have Professor Bromnauta talking about paper writing, Professor Razavi talking about how to do research and do engineering works. Dr. Danielle and Griffiths talk about how to do technical presentations. I like those 3 presentations very much. I highly recommend you to watch them on YouTube. Okay, last, in memory of Professor Willie Sanson, who passed away earlier this year. So I quote his saying in the Circuit Insight talk for the ISSCC 2022. He said, intuition is not existing. Intuition is something you can create by doing it. It's something that you grow. Nobody has intuition, but you can grow intuition. And that's why analog design is a lifelong learning. The only thing you do is to create intuition. Last, I want to thank all my advisors, colleagues, students, and friends. Without them, we cannot accomplish so many good works in the past years. Thank you for your attention. I will be happy to answer your questions.
Well, thank Professor Lu for providing all these vivid examples. That's really inspiring. I wish I could come across this webinar when I was a PhD candidate. That must have saved at least some of my chips and papers. Okay, now let's start the Q&A session. And if you have any question, please use the Q&A panel. We get one question. So the question is like, sometimes the ideas won't work as expected. So how and when should we decide the termination of the exploration?
You mean the name of the?
No, the idea. Like sometimes we
terminate.
Yeah, like when should we terminate and how should we do that?
I think you should discuss with people. You should discuss with your advisor. and also your peer students. Of course, like Professor Willie Sanson said, intuition is something you can grow. You should build your integration by doing it. So by doing it, we need fundamental knowledge, and we need to have hands-on experiences. We need to do simulations, and then we need to analyze the simulation with background knowledge, and we need to discuss with people. So yeah, I think it's a long-term process, and like I suggested, if you cannot solve a problem for a long time, like you have a problem, you cannot decide it, you consider it for a week, for a month, you'd better to talk to someone else. You talk to someone that you trust. Talk to other people to discuss with them. I think they can help you. Don't simply rely on yourself. It's a teamwork. Yeah.
I see. Thank you, Professor. And the next question is for someone who is transitioning from students to a faculty member. What advice will you give them, like for building the research ideas?
As a professor, actually, when I first start my career, I would say it will be safer if we have two legs. I mean, we can have some students working on old problems with new solutions, like we work on DC-DC audio regulators. We can we have a lot of experience in these old applications. So we have circuit design techniques that we can publish this type of paper. On the other hand, we should also look at new problems that may have larger impact. Actually, in terms of paper publication, like I just said, it will be easier to have to work on new problems, new areas. It's not a good example, but if we use old solution to solve a new problem, we can already publish a paper. And then after we work on this new problem for like a couple of years, and then we accumulated some knowledge, we will have new solution for new problems. Then that's better. That's of course better. But one thing I want to mention is sometimes I repeat is new problem is not necessarily a good problem. It's not necessarily a real problem, right? Maybe after 3 years or 5 years, many people study the new problem and then find, okay, this is a fake problem. There are some fundamental limits for this new problem. Then we have some risk. So to reduce the risk for professor, because professors supervise a number of students. If you have, for say 6 students, 10 students, you can divide half of them working on old problem, new solution, half of them work on new problem, new solution. And then as a professor, we can push the student to come up with, to summarize the new solutions into new theory. Eventually, so for senior PhD students or for postdocs, they may be able to come up with new theory after they work on this area for like 5 years.
Right. Okay, I totally agree. And like in the webinar, you mentioned the upward spiral, right? How could we know if we are extending the spiral, not the other way around?
This spiral is talking about ourselves, right? This is about our personal capability, our knowledge. So I think it will not go downwards. As long as we remember, as long as we can remember everything we learned, at least we can go up. It's only the speed and the dimension. Can we go wider? Yeah, can we go higher and faster? Yeah.
Okay, I see. And then maybe due to the time limitation, one final question. Like how do you define the new technology versus the hot topics, right? Like sometimes we see the new topics or hot topics comes in. Like how do you okay, so the technology like and the hot topics hot topic, yeah.
I think it will. We should, first of all, we should embrace the new technology. But because there are so many new technology, especially in recent years, the AI is boosting. As an analog circuit designer, at least for me, it's impossible for me to change my direction to do AI research, to do a large language model. The young people can do that, right? But for circuit designers, at least we should try to use new technologies, the advanced technologies like the FinFETs, GAA FETs that give us more capabilities to design more powerful circuits. We also try to learn how to design circuits with AI, with design automation, but I'm not sure whether this will be actually in large companies. I think they already have such AI tools to generate some basic analog circuits. Actually, one thing I want to say is actually in the past we think artists may not be easily replaced by AI, but right now I would say artists may be the earlier ones to be replaced by AI. Of course, there are some really high-level artists, but for the middle-level artists, I think AI can do a better job because AI knows what people like. For the question, I think we should embrace the technology. We should try to get the most advanced technology we can have, and then to design circuits based on those new technologies. That then we can have new design methodologies to have better circuits. Yeah, I think it's a big question.
Okay. Thank you, Professor Lu. And I think due to the time limitation, let's conclude the Q&A session. And on behalf of the organizing committee, I would like to once again thank Professor Lu for spending time with us and sharing your insights and experiences. And that's indeed, I feel like it's a wonderful talk. And as noted earlier, this webinar will be available at the YouTube SSCS channel. And that concludes today's webinar. And thank you and have a great day. Bye.
Thank you. Bye-bye.
Thank you, Professor.
Bye-bye.
Bye.
Yeah, bye-bye.